Identify the following pair of relationships among the OH group in glucose as cis or trans in the species provided. So now, it says that OH, so they've labeled them. You see that this OH is 1, OH is 2, and then this also OH is 3, this OH is 4, and then this one is 5. So OH1 and OH3, OH1 and then OH3. So now OH1 and OH3, you see that, so let me write it here, OH1 and OH3, which is 1, 2, 3, 1, 3 relationship. OH1 is in the equatorial position, and OH3 is also in the equatorial position. So let's write the key down. We've already established that for a 1-2 or a 1-4 relationship, a cis is an EA or AE, and then a trans is an EE or AA relationship. Then for a 1-3, a cis is an EE or AA position. Then a trans is an EA or AE position. So we are talking about 1-3, and this 1-3 is EE, is an EE because this is an equatorial position, this is also an equatorial position. So 1-3 EE is a cis. So that means that this is a cis. Then OH4 and OH5. OH4 and OH5, the relationship between them is a 1-2. And then for a 1-2, you see that this is in an equatorial position. This is also in equatorial position. Then for 1-2, EE is a trans. So this is a trans. Then let's come to OH2 and OH4. So OH2 and OH4. So you see that it's 1, 2, 3. It's a 1-3 relationship. So for 1-3, the 2 is in equatorial position, and then the 4 is also in an equatorial position. So 1-3 EE. 1-3 EE is a cis. So here's a cis relationship. Then now, the last one is a 1-5. 1-5. So this is 1, 2, 3. So this 1-5-2 is also a 1-3 relationship, and that 1-2 is also an EE. This OH is in the equatorial position, and this 1-2 is also in the equatorial position. 1-3 EE is a cis relationship, and for that matter, this is a cis relationship. And then the second part of the question says that we should state 2 reasons why cyclohexane exists as a chair conformer and not a boat conformer. So the first thing is that the boat conformer has unfavorable steric interaction between the 1,4 hydrogens. So the boat conformer looks like this. Boat conformer cyclohexane looks like this. And then there's a proton here, and then there's another one here. And there's another one here, and there's another one here. You see that there is a steric interaction between these 2 protons and also these 2 protons. So it makes the whole ring unstable. And that's how come it would exist more as a chair conformer than a boat conformer. And then the second reason is because of the higher energy of the boat conformer. It forces the protons in eclipse position. So remember that from Newman projections, we've already established that eclipse position of atoms makes the molecule unstable, make the boat conformer very unstable, and therefore it will form a chair conformer. And then here he says that state which of the following compounds are conformational, constitutional, geometric isomer, enantiomers, or identical. So you can see that between these 2 pairs, what are they? You can see that this chlorine has been rotated to this side. And then when that happens, this methyl group will come here, will be at this side. And then the proton will also be at this side. So you can see that these two are what? Conformational. So these two are conformers, so conformational. Then what about these two? Now, these two, you can see that there's an OH here, OH here. There's a CH3 here, CH3 here. There is a deuterium here, and there's also a deuterium here. Then there is a CH2SH, but here it is rather an SH before a CH3. So you can see that these two, they differ in terms of how the atoms, the positions in which the atoms are connected to each other. And anytime you talk about positional isomers, you are talking about constitutional isomers. So these two are constitutional relationship. And then these two, this proton is in the equatorial position, and this one is also in the equatorial position. Then there is a ring flip, and it is a 1-3 relationship. Then there's a ring flip, and this one comes into the axial position, and this one also comes into the axial position. So you can see that these two are what? Identical. So this is an identical relationship. So these two are identical. And then let's talk about this. So here is an axial position, and this is our equatorial position, AE. There is no ring flip, still 1-3. So, and with the 1-3, this is an equatorial position, and this is also an equatorial position. So AE in a 1-3 is what? Is a trans isomer. And then EE in a 1-3 is a cis isomer. So cis and trans isomerism, we are talking about what? Geometric isomerism. So these two are what? Geometric. Identify which of the following molecules are cis or trans. So the key is always important to identify which molecules are cis or trans. Remember that we have already established that for a 1-2 relationship or a 1-4 relationship, the cis is an EA or an AE. Then the trans is an EE or an AA. Then for a 1-3, we said a cis is an EE or AA, and then a trans is an EA or AE. So let's come to this one. You see that this is a 1-3 relationship, and then this methyl group is in an equatorial position, and then this CH3 too is also in the equatorial position. So 1-3 EE is what? A cis, and therefore this is a cis. Now let's come to the B part. The B part is a 1-4. So 1-4, this CH3 is in an equatorial position, and this one is in the axial position. 1-4 EA. EA in 1-4 is a cis. So this is also a cis conformer. And let's come to this. This is a 1-2. This is in an axial position, and this is also in an axial position. So 1-2 AA. 1-2 AA is a trans. So this is a trans conformer. Then this is a 1-3 EE, because this is in an equatorial and this is also equatorial. 1-3 EE is a cis conformer. So this is a cis conformer. And then this is also a 1-3 This is also a 1,3, and they are both in what? Equatorial positions. So this is also a 6 conformer. And then this is a 1,4. You can see that this is a 1,4, and that is also EE. 1,4 in EE is what? A trans conformer. So this is a trans conformer. So 6 conformer, 6 conformer, trans is trans conformer. So with this, it says that provide structures to form a pair of constitutional, conformational, geometric isomers or enantiomers. So with this chair conformer, he's looking for the constitutional conformer. So you can see that this is what? A 1,3. Sorry, a 1,4. So what we can do for constitutional, they only differ in their position of attachment. So for the constitutional, we can draw a 1,3 constitution of this. So we can do this. So with this chair conformer, so we can put a CH2 Cl here, and then this CH3 we can bring it to a third, so CH3. So you can see that this is a constitutional isomer because they only define their point of attachment. This is a 1,4 and then this is a 1,3. Then it talks about this conformational. So you can see that this is a staggered conformation. So we can draw an eclipse conformation of this molecule. So let's draw the eclipse. So this is the carbon in front. So there's a CH3 here. And then here's a proton. And then this also is CH3. And then this is the carbon at the back, which is this. And because we are drawing an eclipse conformation, we can put a CH3 here. I can put a proton here. And then we can also put this proton here. So this is a conformational isomer of this one. So this question says that draw the most stable conformations of A, ethyl cyclohexane. Then B is 3-isopropyl 1,1-dimethyl cyclohexane. And then C is 6 1/3 butyl 4-isopropyl hexane. So let's start with the first one, ethyl cyclohexane. So a cyclohexane that has an ethyl group on carbon number 1. So let's draw the most stable conformation of this. Since it is only ethyl as a substituent, then we can put the ethyl group at carbon in the equatorial position. So this is the most stable conformer. Then the second one, so for ethyl cyclohexane, this is the stable conformer. You see that the ethyl is in the equatorial position. Then the second one is 3-isopropyl dimethyl cyclohexane. So 3-isopropyl 1,1-dimethyl cyclohexane. So that means that we have a 1,1-dimethyl here, and then we have a 3-isopropyl. So this is an isopropyl. So this is an isopropyl group, and then it's on carbon number 3. So what is the most stable conformer of this molecule? So this is the ethyl, the 3-isopropyl 1,1-dimethyl cyclohexane. So let's draw the most stable conformer. So we have a methyl on 1,1, an isopropyl on carbon number 3. But we need to give precedence to the isopropyl because it is the most bulky group, and therefore the isopropyl must be on carbon number 3. So that means that this methyl 1,2 dimethyl, one will be on the equatorial position and the other will be on the axial position. And then the isopropyl group will be in the equatorial position on carbon number 3. So this is 1, 2, 3. So this is the most stable conformer. Then the last one is 6-tet-butyl 4 isopropyl hexane. So let's draw hexane. And we are talking about a 1-tet-butyl. So we have a tet-butyl here. Then we are talking about then a 4 isopropyl. So there is an isopropyl group here. However, we need to show the stereochemistry because it says it's a 6. And since it's a 6, we could convert this into wedge bonds. So this could be converted into wedge bonds. So as you can see, this is a 6. So let's draw the most stable chair conformer of this 6 compound. 1,4. 1,4 in a 6 is an EA or an AE. So if it is 1 here, so we need to put the most bulky group in the equatorial position. And the most bulky group is the tet-butyl. So that needs to go in an equatorial position. And on carbon number 4, since it's a 6, then it's an EA. So if this is in an equatorial position, then the isopropyl group must be in an axial position. Therefore, it will look like this.